That was my first sort of foray into, okay, how do we reduce our training costs by moving to AMD, was porting the kernels and then plugging them into our training stack, which we did.
All right, welcome to Beyond CUDA. I'm your host, Jeff Tatarchuk, co-founder of TensorWave, the AMD GPU cloud. Today on the show, we have Quentin Anthony, who's the model training lead at Zyphra, where they're building MyOS, a multimodal agent system for enterprises combining advanced research and next-gen neural network architectures, long-term memory, and reinforcement learning. Quentin, welcome to the
Thanks
show,
for having me
man.
on.
Glad to have you. Yeah. Before we dive into some of the stuff that you're working on at Zyphra, take us back to the beginning, man. What got you interested in computer science and AI?
I see. Well, I started in physics. I did my undergrad in physics, and I was doing all my research in quantum computing. And it was all experimental. So I was in the dark lab all day long. I was doing optics for quantum computing. And I just decided I kind of hate wet lab kind of work. And I much prefer doing more thinking rather than a lot of like tinkering on mirrors and everything else. And I feel like there's a better ratio of like thinking to the grunge work in computer science. So I switched over for PhD and then never looked back.
Nice. And what were some of the stuff that you were working on when you were there?
During PhD? Yeah,
Yeah.
well, I did my PhD, in HPC, so with a focus on networking. So a lot of, like, MPI level optimizations, a lot of cross-stack stuff with a focus on distributed computing and networking. So we did different parallelism schemes. Back in the day, it was all, like, pipeline parallelism for ResNet, and trying to spatial parallelism, really large, like, images and stuff. It was all CNNs, old GPUs as well. So, this was Oh god, this was like Volta GPUs, Pascal GPUs, and so on back in the day. And then it was very good timing because then everything else blew up and Transformers Attention Is All You Need came out. Everyone sort of moved over to that. Everyone suddenly needed all of this distributed computing stuff that we had been working on. Things just kind of snowballed.
Yeah. I mean, what made you decide to go into the networking side of things? What did that kick off?
I mean, that was from the start. I mean, when I was in undergrad doing physics, I took a class on distributed computing and AI and all of that, and that's why I jumped in there straight in from the start. Just seemed interesting, seemed like hard problems. Scale mattered a lot, and you're a subject matter expert that's below like application layer, then you sort of jump around a lot of different applications. So you could work on like physics simulation codes, and the next day work on deep learning. And even within deep learning, there's all kinds of different modalities and different challenges they all pose. So it just seemed like a good way to keep things fresh.
I remember we were talking earlier that you had done some work with the Oak Ridge National Lab Frontier supercomputer. I believe, what do they have? The MI250s. Tell us about that and what you're working on with that.
Sure. Well, I mean, in HPC land, we work a lot on government supercomputers. So it used to be these huge clouds from industries weren't really the standard. They weren't really topping the top 500 list of biggest supercomputers. And when the government was sourcing compute, they always tried to move vendors so that there's no vendor lock-in over time and the taxpayer money doesn't all go to the same company every single build out. So we were used to like churn of different systems. So when Oak Ridge announced that they, were with AMD, it was not really a big big deal. It was just, okay, this is the new GPU and we all deal with it. So before Oak Ridge went online, I was collaborating with Oak Ridge engineers on porting Flash Attention. So Flash Attention 2 had just come out and we were trying to get that ported to an AMD system. That since I didn't have access yet, these were like kernel patches going back and forth over email. So I would send, okay, try this diff and this text file, and then they would try it and then back and forth because I'm not an employee at Oak Ridge, so I can't go on the system yet. We also had to sort of rebake parallelism schemes in because people are used to doing, okay, you have 3D parallelism. Some parallelism schemes require more communication bandwidth than others. And GPU clusters have this nice property of within the node, you have these extremely fast interconnects like AMD Infinity Fabric or NVIDIA NVLink. And then across nodes, you have a still fast but relatively slow interconnect. Whereas on AMD Frontier land, you have 3 levels. So you have 2 GCDs on a GPU that can communicate very quickly across each other. There's 4 links. And then across GPUs, you have still fast but slower interconnect. And then you have across nodes. So all of the parallelism schemes that we had developed, assuming a 2-level topology, had to be reworked with this new scheme because the 2 GCDs on a single GPU could still access the same high bandwidth memory space. So like you still have that constraint needs to share memory, but there are also distinct ranks. There's a lot of new challenges that we had to build around, and that was my work for a little bit. I have a few works on it.
What year was that?
Oh, good. You're quizzing me. Let's see. I had the papers up. That would be like 2023, 2024, those 2,
Okay.
yeah. But like early
Okay.
2024
So
was the end of that.
nice. So not too
Mhm.
long, not too long ago. Still fresh. Well, interesting. So then finished up your work on working on the 250s, and then I got picked up by Zyphra,
Mhm.
and you guys have been working on creating your new model architecture. Share with us what that journey has been like at Zyphra, what it is that you're actually working on, and some of the problems that you're looking to
Sure.
solve.
So, okay, the mission here is to make models that are personalizable, offline. We don't really think that everyone can have a personalized model just via system prompts with the same weights. So the first challenge was how do you make an inference efficient model that works on a variety of hardwares? So both on people's phones, because everyone today has sort of a heterogeneous architecture on their phones. You have like an Apple neural engine that's sort of like a tensor core, and then your laptops now are moving to like NPU plus GPU plus CPU, and then all the way to cloud systems for like enterprise customers. So you have to make the same model perform well on a lot of different hardware. That also includes like cross vendor. So even within cloud for enterprise, you have AMD GPUs, you have TPUs, you have NVIDIA GPUs, and so maybe TPU is a bad example, but you have this Cerebrus wafer scale stuff. So you have a very wide variety of hardware that you want to target, and baking that into a single model or set of models is very hard. So inference efficiency was how do you pre-train a model with inference efficiency in mind across separate hardwares was the research problem that I was brought on to solve. Um, we've made a lot of exotic, weird architectures to get around this problem. So we did the first model was a Mamba MOE called Black Mamba, and then we switched over to a hybrid Mamba and Mamba 2 with transformer blocks. So we found that transformers have like too much attention. The attention blocks across depth are saying these are the important tokens. These are still the important tokens. They're still the important tokens. That's a very expensive thing to remind the MLPs of. It's a lot of flops in memory to do attention. So we instead said, okay, well, let's just explicitly tie those weights together so that they have the same memory overhead. These are the same weights themselves. We just reapply them over and over, and then the rest is all Mamba. And then we have some interesting new models that we're cooking. We're about to release, sort of continuation of the same ideas, though, of training and inferring on exotic hardwares with a focus on inferring on exotic hardwares because that's our bottom line for our customers. Long-winded response.
That makes sense. And how do these hybrid models differ from their traditional transformer models in terms of deployment on the devices from smartphones or edge servers?
Not sure quite what the question means here. So they differ. I'd explain the model architecture change, but you asking just like realistically how do you serve them or what frameworks to put them in? So we
Yeah.
we have our own internal serving stack that are forked off of very popular serving frameworks such as like Llama CPP. We have our own internal version that's optimized for our models. That would be for on-device stuff, so we can get things working on an iPhone or a Samsung phone or whatever else. And then on cloud, I've also forked off of a common like DLM, for example, and then we make them highly optimal to our own models and our own serving needs. We also have the separate modalities. So one keyword you mentioned about Maya at the beginning was that we're targeting multimodal, and currently that's just audio and text. And audio models have very different requirements. So we have our own serving stack for that one, built from the ground up. Right now, we have these sort of disparate, depending on the modality and the class of hardware frameworks that we'll eventually be unifying as time goes on.
I remember you were spending some time working on Megatron and getting Megatron working optimally on AMD. Talk to us about what you did to get Megatron working, and where is it at now?
Sure. So, since Zyphra, we kind of are pre-training and inferring. We are our own customer for training, so we need to reduce costs as much as possible, and we're always trying to find the best hardware for training to reduce that cost because it is very costly to pre-train your own models. We're competing with very well-funded big tech companies, so in that regard, having a kernel and systems team is very powerful. And we decided to use that to find the best hardware with software ecosystem notwithstanding to train our models. And we found that to be AMD MI300X at the time. Still seems very promising. We'll be moving our training stack over to that. So our training stack is Megatron based, and it requires specific kernels like Flash Attention 2 and in Mamba 2. So that was my first sort of foray into, okay, how do we reduce our training costs by moving to AMD? Was porting the kernels. We have a blog post out on this, and then plugging them into our training stack, which we did, and is very doable. I recommend everyone, any other big players that's looking to pre-train, should at least explore this option if you have a kernel team. But the risk to reward is very good.
What were some of the challenges you faced as you were doing it?
Yeah, it's finding just how many kernels have implicit assumptions about their hardware. And very often that implicit assumption is in the current paradigm of compute. So a lot of them have, it's not just as simple as changing like the kernel block size, the number of warps or whatever else. It's more very fundamental assumptions are made in flash attention, in Mamba, and any other kernel you can find today for NVIDIA. And to understand the hardware at a very deep level and the algorithm at a very deep level in order to, you can't just port over the kernel directly. You have to instead build it from the ground up on the new hardware. That was the difficulty. Like, how do we boil down an MI300X and how do we boil down flash attention to its barest subcomponents to the point where we can make it hum on this new GPU?
Yeah, I'll share that article that the blog that you wrote in the notes here. What are you currently excited about when it comes to the future of AI and what you're working on?
I'm very excited about new architectures, and that's an overloaded term. So both in terms of hardware and in models. I don't want to give too much away about what I'm excited on because I'm working on it very hard, and I don't want anyone else to jump in. But I would say continuing down this path of finding the very best inference efficient architecture and then finding the best hardware to deploy those on for pre-training is where I spend. That's why what keeps me up at night. That's where I spend my time. I got to keep those GPUs
Yeah.
humming on something that's new and that will change the model landscape in a non-trivial way. We don't want to just be another transformer written on or trained on common crawl and then with a standard post-training strategy from someone else. We kind of need to push the envelope forward just to survive in such a competitive landscape. So doing exciting things that might not work out in terms of hardware and model architecture is what we're doing all the time.
You beat me to it. That was the next question I was going to ask is what you're excited about, but then what does keep you up at night? What is the biggest challenges that you're currently facing?
What keeps me up at night are weights and biases, loss curves, and notifications on whenever
Mm.
they spike. I would say that anytime you're working on model architecture changes and you're training a new model, you don't have the compute to test it all out. You can do a lot of small ablations on smaller models and sort of say get some intuition that this okay will probably work out fine. But when you kick off the big $1 million training run that will finish in 2 months or something like that, if it dies and doesn't do well, then you know it's a very expensive mistake to make, and that definitely does keep me up at night.
Mm.
Is sort of steering the ship in the way that that doesn't happen, and luckily so far we've trained multiple model suites without that happening.
And what are some of the things that you're doing to ensure kind of plugging the holes in that regard? Because I've heard stories of people, they just like, they'll stay up. They'll set times where they'll stay up 24/7 to make sure, everything's time stamped and everything's, doesn't go down. So you don't waste money and have to start all over again. What are some of the things that you guys are doing to
Well,
ensure that?
we have a lot of very passionate people who are sort of looking at those same loss curves I mentioned before around the clock. We do, as I mentioned, they're not perfect, but we do a lot of smaller scale ablations as much as we can. And then I would say our methodology is we're not really rooted or moored to any architecture assumptions, but at the same time, nothing is a crazy idea. So we make a lot of like solid roof shots instead of making some huge moonshot YOLO run, risk the whole cluster, risk the whole company on something. We instead very like slowly uh, prove out with each new model architecture what are the next sort of small changes that we can make. So, for example, Black Mamba was our very first model. It was exploring Mamba more than MOEs because we had trained MOEs before then. And then the first Zamba suite was okay. Can we make a dense model that explores out this space of attention blocks are correlated across depth, like I mentioned. So can we tie the attention blocks together? How much attention do we actually need? Let's make a conservative guess and then train a model and get a good one out of it and then move forward.
How much do you need?
Attention. So 6 Mamba
Yeah.
blocks and then an attention block. So we have, I think it was off the top of my head, like 17 invocations of a transformer layer, whereas Mistral 7B was something like 30, significantly less. From Zamba 1 to Zamba 2, it was the change of, okay, well, Mamba 1 to Mamba 2 blocks. We first proved that out at small scale. We also completely revamped our data set. So making bold changes, but not too many at once, to where you sort of keep an intuition of the system, keep grounded, move to the next roof shot is kind of how we do things.
What's next for you guys? Like, what do you see that coming down the pike? And
We are moving our training cluster to AMD, as I mentioned. So that is a big
it's
migration.
exciting.
Yes, very exciting. In the same way, we're sort of trying to see how we can best use the heterogeneous compute paradigm to serve us, and that we do like development on very easy software ecosystem GPUs, and then we sort of do a one-time transfer onto the AMD cluster, which has a better cost, and then we kick off our training on that lower cost system. So we sort of remove the friction of trying to get model architecture people to figure out a new software ecosystem while still benefiting from that most of our compute cost spend going towards a cheaper type of GPU. So that's something I'm currently setting up, taking a lot of time.
What do you see as the biggest advantages that you're going to be able to utilize switching to AMD? Because I know some people are like they're afraid of switching to AMD due to the switching costs or the unknown unknowns that could be around the corner. But what do you see as the advantages of making that switch? What are you currently excited
Yeah,
about?
well, like I mentioned earlier, you can reduce your risk by doing a lot of tests. Like we didn't just like blaze our current cluster to the ground and then move entirely to AMD. We would be down for months. We instead worked with you guys and other providers and did like small test runs with small models, get the kernels moved over. That itself took some time, took several weeks. Then move our training stack on top of those kernels, that sort of thing. The main benefits, as I mentioned before, they are cost. The another one is that the AMD MI300X in particular, if you were to compare it to like an H100, has a lot of very amenable hardware properties like higher HBM, so much higher VRAM, and that just directly yields to less parallelism, leads to higher batch sizes when talking about pre-training. So it makes our remember at the beginning I talked about during my PhD, I did everything on parallelism schemes and like how to distribute this thing. I know communication from those parallelism schemes is like a necessary evil, and doing less of it on a higher VRAM GPU both reduces my training time and also reduces my dev time significantly because now I don't have to have an army of Megatron engineers who are able to port tensor parallelism over. We don't need tensor parallelism at all, right? Because the whole model fits, that sort of thing. So VRAM is a big one, as I've been waxing poetic. Actually, once you do the initial movement, the ROCm software stack is not as scary as people say, I would say. To be honest, a lot of the shortcomings are on those like initial, how do you get on the ground running? What Docker container is good? What PyTorch fork is tuned? That sort of thing. Once you find those, things tend to click into place. And I think a lot of the momentum here recently at AMD has been people like Anush who come out and make but much better user guides, much better on ramps, so that people can get that initial step over and see that things are much rosier than they've been told in the past.
Yeah, exactly. I know that was a big piece is developers' initial out of the box experience wasn't the best. But if you do have the correct Docker container with all of the right versions in place, which is what we focus on when we're working with developers, is giving them, after we've tested, the best configuration. It's great to see the progress that AMD and Anush and the rest of the team have made in keeping up and moving quickly, which is exciting. That being said, we know that there still are issues that have to be, overcome. What do you see? Like, if you could wave a magic wand and magically fix some of the things that need to be worked on. I know you're focused specifically on the training side, but if you could wave a magic wand and have somebody else solve a problem that could help move the needle exponentially, what do you think that would be?
I think FP8 is still this big mysterious thing that no one. It's sort of a mix of things. So the people who have figured out anything are very tight-lipped about it, and the people who are sharing and shouting from the rooftops about FP8 working are not reproducible. And like as soon as H100 came out and they introduced FP8, they sort of had these very smoking gun statements about how we see no issues with convergence at all with FP8, gaslight everyone into thinking that things just work. Almost have to like go out and directly ask people who have done their own compare notes and compare ablations and sort of things, and there's fewer people training on AMD, so there's fewer notes to compare with. And if AMD themselves sort of spearheaded a investigation into what exactly can be FP8, what can be communicated in FP8, what can be computed in FP8, and get some more clarity, I think that would lead to a pretty good edge on the training side, because it's still kind of hard, no matter on what GPU you're working on right now, to conclusively say what can be used and what can't without a ton of ablations. Yeah, that's the gist.
So we've been tasked to help with on the AMD side is we're deploying an 8,000 GPU cluster of the MI325 specifically for training and solving some of those bigger problems to make them as performant and efficient as possible. And FP8 is definitely a big one.
And another one is sort of the you should shout from the rooftops about Rocky, because coming from HPC, Rocky used to be this like I don't know uglier sibling of InfiniBand, but things have changed, and Rocky has been proven out by a lot of players, including TensorWave, to be at the same or better level than InfiniBand in some cases, and it's much cheaper. I think just a bunch of basic communication blog posts or papers just showing that, okay, changing the same parallelism schemes ported over to a Rocky-based system. These are the micro benchmarks of the specific collectives that you need for parallelism. These are the parallelism schemes themselves working. I think that would convince a lot of people like me who are used to Rocky being in a place in your head that's not something you train on.
Interesting. Yeah, that makes sense. And that is some of the stuff that we will be working on is producing some of those papers and showcasing Rocky V2 at
I
scale.
remember you and I think it was Derek sent over a bunch of Rickle test results with Rocky at scale, and I was like, "What are these guys doing? Like, how do they get such good results?"
Derek and his
I
magic.
know, yeah, yeah, but
Getting the Rickle nickel piece is not an easy task to optimize for. And but we're close and excited about the progress that's being made. Well, the podcast is called Beyond CUDA. Now we acknowledge and appreciate the breakthrough that CUDA has made to get us to where we're at today, and know that there's more out there to be developed. When you think of Beyond CUDA, what does it mean to you?
I think it kind of means NVIDIA's not going anywhere. But that doesn't mean that a monopoly will continue with this scale. I think it's silly to think that all these other companies, all these other big tech companies working in-house and GPU providers like AMD would just not make enough progress to be viable options by the time it's 2025. I think that it's hard to sort of talk to people that AMD and these other competitors are viable now without sounding like a shill, but it's here, and that people should go and at least test these other GPUs. Big people like me who have to spend a lot of time on pre-training compute, people who are have a high inference bottom lines should at least test these other GPUs. They should at least consider them. This sort of you're kind of laughed out of the room for even saying maybe we should try on AMD, maybe we should try on Cerebras, maybe we should try on Grok or something like that. Is no longer you lose if you're this close-minded now. And any sort of tiny edge that I and other people can squeeze out by going to those hardwares will be used against you.
Yeah, that's true. That's true. What is it? Nobody got fired for buying IBM, and the same thing is for NVIDIA. Now that others are looking for other solutions, it's easy. It's easy to get the price down, but improving the experience and the developer experience and performance, AMD has done a great job. I'm at the risk of sounding like a
Yeah,
shill,
these the same
but
sort of thought patterns of there are new ideas that are not acceptable are the same reason that we can make significant improvements in the model architecture space as well. So instead of just being laughed out for, oh, are you going to fuse together a Mamba block with some shared attention block or something like that? Having the courage to go and try these crazy things is painful and takes a lot of time. But there are things that people are overlooking because of this thought pattern. I just wanted to put that in there. Continue.
yeah, exactly. And what are some of the things that, as because we've had people, they've jumped on, they've tested AMD, and they just jump right out. They're like, "Oh, this is not what I was expecting," and very comfortable on what they're doing on NVIDIA. What are some of the things that they should be looking for or testing for as they jump in, and what has made it easier for you?
They should just be testing on what specifically they need. So, like, one example is that if your business model requires you work on dense transformer models, then dense transformer models tend to perform really well on models or on hardware that have powerful tensor cores, like NVIDIA GPUs. Whereas models that are more bandwidth bound, both on interconnect if they're really large, or memory bandwidth, if there's something like an MOE, where you have to constantly be paging for memory, those make a lot more sense on AMD. So, like, it's not everyone should just be for no reason at all locking into whatever GPU on either side, but instead boil down whatever your model is or whatever your use case is to its barest components, down to kernels, down to flops and flop bytes at the end of the day, and look at the hardware properties for both, decide which ones give you the better performance for those, and cost, of course, has to be included in this, and then try and squeeze that expected performance out and get as close as you can to it. And what I'm trying to say is that you can get most of the way there easier than people think today.
What do you need as you're developing and building this? There's a lot of open source stuff that's out there, open source ecosystems that are building and developing. Obviously, everybody's trying to hire the best kernel engineers to help with this porting. But what are some of the things that you need or Zyphra need as you guys are building out your
Well, I
products?
will take a handful of those kernel engineers. So if there's any kernel engineers listening who have worked on AMD before, then we would love to talk to you. Just really anyone working on low level hardware architecture stuff is important for us. Low level kernel writing and all of that. What I would love to see is more papers, more classical HPC analysis, systems optimization. So I want to see kernels like flash retention. I want to be able to compare notes. It took me several weeks to port flash retention to MI300 and flash retention 2 to MI250 because there's no one else out there who are putting these things out. I would love to see more people just boiling down. This is the hardware that I was given, and these are like the fundamental changes in my kernel I made to make that hardware performant. And putting that in the open, I think, would be really impactful.
Yeah, that makes a lot of sense. We've toyed with doing a Beyond CUDA Discord where we can collaborate on some of these things, and at Beyond CUDA make it more of a research paper presentation of some of the things that are being worked on, but being intentional about some of the problems and stack ranking the problems that we're solving and working on together to help move the ecosystem together.
One other thing on that is that any sort of kernel language that is high level like Triton, their backends for these alternative architectures are definitely still lacking. So, for example, I tried to write the flash attention and Mamba 2 kernels in Triton and found myself fighting with the Triton compiler more than I was with the actual optimization itself. So say like you want to make some optimization in the kernel, not only do you have to understand the hardware level what optimization you're making, you also have to understand the Triton compiler at the level of like a maintainer to keep it from breaking everything else. So there's a lot of work to be done. A lot of these are just like a huge accumulation of patchworks in a lot of the distributed training frameworks like Megatron and a lot of higher level kernel languages that compile down to GPU instructions like Triton. A lot of that in between, a lot of the patches, the patchwork from all these people kind of coming together and building in the open, that needs to happen. Like we need to patch all of these holes that currently exist, all these small edge cases that people find when there's sort of an army of us working together. That needs to be done.
Yeah, I like it. Well, there's clearly a lot to be done, but it's great to see the progress that has been made, and I'm excited about the progress and the things that you've contributed to help get us here. And the champion, I know you've been, a champion in the background, helping move the ecosystem forward. So I'm grateful for the work that we've done together and excited about continuing to work together in the future. With that being said, Quentin, thank you for being on the
Thanks
show.
for having me.